I'm Nurul Iziani. So today I will present on system design with high-level synthesis. So in this project, we are given a baseline code on matrix multiplication with 4 by 4 matrix size. So we will do high-level synthesis with using Vitis HLS tool. So in my case, I'm using version 2024.1, and yeah, so I will go through on the result of my project. So this is the baseline design code. This is the C++ code with input matrix A and B and an output of C with all with 4 by 4 matrix size. So in this case, we just do multiplication between each row and column, and then sum the multiplication and get the output. So in my optimized design, I'm using array partitioning, pragma. So for variable input A and B, I'm using array partitioning with complete type, which will split each of these elements, in this case is 16 elements, into each individual registers. So this should be able to improve the performance and enable parallelism into the design. And also I enable HLS pipeline for these 4 loop iterations. So I have also designed a C++ test bench. So basically this one is just to test the functionality of the design. So in this case, I have one function to compare the matrices, and I have the expected output to compare the result from the design with this hard-coded expected outputs. So input A and input B has been defined with this value, and so this value will be give as an input to the design function here, which we call here in the macmol in the C test bench main code. Yeah. So and then after we input in, and then we get the output of C, we will compare the matrix in these functions and print out the passing or fail message. So if it's passing, then we will be able to see that the multiplication is done correctly. Yeah. So for both design, I will go through this C++ test. I will run the C simulation first, and then I will run the synthesis if the result is correct. So next slide is I will show you the simulation log. So basically both baseline design and the optimized design obtain the same result. So for both design, I am able to see test passes and matrix multiplication is performed correctly. After that, I run a synthesis, but then I will show you on the timing diagram first. So in this case, I'm not able to zoom in perfectly, but all in all, I think you can see that for the baseline design, everything works not serially, because automatically the HLS tool, Vitis HLS added a pipeline into my code when it does the synthesis. So as you can see, it's not really serial, because after one iteration, one clock cycle, another input of data coming in. So it go alternately between the input A matrix and input B matrix. and then you can see that each of the clock cycle has the output for the C matrix. And then it took around 32 clock cycles to finish the whole operation of this 4x4 matrix. Yeah, so this is the baseline design, and for optimized design, achieve a better throughput and latency. It's a bit small here, but as you can see here, you see up here is the output, which is the matrix C, and down here is the matrix A and B. So in my optimized design, I'm using a complete array partitioning and a pipeline mask. So for complete array partitioning, I can see that the input matrix A and B here are being split into 8 pipeline registers, and each pipeline register holds 2 elements from the 4x4 matrix, input matrix. So you can see this line is one of the address of the input B. So 121212 is the address. So basically, these are the elements that has been input into each of the pipeline registers. And once all this ready, then the design will compute the output matrix C, and output matrix C are split also into two pipeline registers, and each pipeline contain whole 8 elements of the 4x4 output matrix. So it's also a perform parallelization here on the output C, even though I didn't define any array partitioning for the output matrix C. So this optimized design achieve a better and lesser latency compared to the baseline design. Next, I will show a table to compare between baseline design and optimized design in terms of performance and resource utilizations. So as you can see here in the critical path delay, which is the maximum of time for the data to be processed between one register to another register. So in this case, it's achieved the same CPD and frequency, max operating frequency. This is because for both design, the Vitis HLS tool did optimization on by applying pipelining to both design. Even though in the baseline design, I didn't define any prop mask, so it's just automatically define the pipeline registers for me. So for both of these, CPD and Fmax are the same, which is constants with 0 difference. And latency and throughput, you can see a very huge difference here, where latency for optimized design only required 9 clock cycles to finish all of the operations, with 71% of improvement compared to baseline design. And in terms of throughput, so the optimized design can perform 17.04 million operations per second. So it's like 200% difference compared to a baseline design. However, as we expected, since we are using a complete array partitioning, so we are introducing a lot more registers to be used. So in this case, the number of LUT and flip-flop and DSP has been increased significantly. So it is more trade-off. So it's a trade-off between a performance and a resource utilization. So I also put here that the pipelines are being defined in baseline design. Yeah, it's in blue color because I didn't define it, but the Vitis HLS tool is intelligent enough to optimize the design for me to achieve a better result. Yeah, I think that's all for my presentation. Thank you.